Alright, this is chapter 6 through 10 review for a physics test. I'm not going to write the question, but I'll read it and then we'll go after it. Question number 1 says, how much work is required to move a 1,700 kilogram crate by pushing it 3.5 meters across a rough floor without acceleration, if the effective coefficient of friction is 0.72? So I got a box. I want to push it this way. There's a force. I want to move it a distance of 3.8 meters. As soon as you talk about that, your first thought should be about work, because it said work, which is force times distance. The issue here is really, how do you know how much force is being applied? Well, it said without acceleration, which means there has to be a force that cancels out my effort, and that would be the force of friction. So we balance out. Well, the force of friction is, by definition, mu mg for all horizontal surfaces. Mu times the normal force, which is mg, again for those horizontal surfaces. So this is really mu mg times d. Mu is our coefficient of friction, which is 0.72. M is 1,700, that's the mass of the box. G, of course, is 9.8. And then D, our distance, is 3.5, not 3.8. I misspoke earlier. So 3.5. I'm just going to throw it all in the calculator, and the work done to do that is 41983.2 joules, which, even though it's not necessarily graded, I'm always going to try to do sig figs. That would be 2 sig figs for the problem. 42,000 joules of energy is being done, or work is being expended, energy expended, so the work done. Okay, question number 2 says we've got Fernie going down with his frictionless snowboard down an incline. The surface says he's going down a hill at a 22-degree angle of decline. That's also means that it's here. A declination angle would be right here, and so its elevation angle is the same thing, 22 degrees. If the length of the hill is 110 meters along the surface here, we want to know how fast will he be going right down here if he starts at a velocity of 3.2 and lets gravity do all of the work. Well, if gravity's going to do all the work, then what that means is that the potential energy change, okay, the change in potential energy is going to be what gives him a change in kinetic energy. Okay, that potential energy is going to become kinetic. And so if we look at the initial setup right here at the top of the hill, he has both potential and kinetic energy. So his potential energy would be mgh 1 plus his kinetic energy is 1/2 mv1 squared. That's his energy at the top of the hill. At the bottom of the hill, he doesn't have any potential energy because he's at the bottom, but he does have 1/2 mv2 squared. So he has a new velocity. In this question, we notice that all of them have the m, which means I don't have to worry about the mass of Fernie. I just need to plug in these numbers. The big issue right here is, what was the height initially? Well, height is going to be measured vertically, but I have this diagonal measurement. So I'm going to have to do a little bit of trig. Based on the fact that I want the opposite from 22 and I have the hypotenuse, I'm going to do the sine of 22 equals, we're going to call this h over 110. If we times by 110, we learn that the height of the hill is 41.2 meters. That makes this 9.8 times 41.2 plus 0.5 times the velocity he had to start was 3.2 squared will equal 1/2 v2 squared. I'm going to simplify all of this on the left. I'll times it by 2 and I'll take a square root. That's the half and the square. If I put that in the calculator correctly, one piece at a time, I'm going to end up with 28.5965, and I'll round that to roughly 29 meters per second. Alright, if we move on to question number 3, it says Derek's got an engine. We want to know its power rating. It takes a time of 1.5 seconds to move a 95 kilogram box up 4.2 meters. Okay, and we want to know what's its power rating. Well, power is work done over time. Now work, it depends on what kind of force we're applying and which direction we're applying it. Think of work as it's a change in energy. If I lift a box, that means it's going to gain a bunch of potential energy. Well, the potential energy gained would be equal to the work done. So maybe a change in potential energy here over time. The change in potential energy is going to be mg and then times the change in height. M being 95, g being 9.8 of course, and then the change in height is 4.2. All of that divided by the time it takes to do that, 1.5. If I throw that in the calculator, I get roughly, when I round, 2,600 watts of power. Again, I'm going kind of fast, but you can look at these questions in slow-mo by hitting pause and reviewing the question yourself. We'll also cover it in class. All right, question number 4. We've got 2 balls. This is a little bit confusing because ball A is headed west and ball B is headed east. All right, so we're going to have a collision and we want to know what happens to ball B and ball A after. Do they both end up going left? Do they both end up going right? Do they bounce off each other? And how fast are they moving? Okay, and so the formula is MAVA1 plus MBVB1. Because they are in an elastic collision, so that means they're a bouncy version of the equation. It will equal MAVA2 plus MBVB2. Essentially, they're not going to stick together. I'm going to start filling in. The mass of ball A is 1 kilogram times its velocity. It's 1.5 west, so I'm going to call it negative 1.5 because that's to the left, plus the other ball is 2.3 kilograms. I'm going to multiply that by its velocity of 6.3 to the east. That will equal 1 times VA2 plus 2.3 VB2. The problem is I don't know either of the two exit speeds. So there is another equation that I can use, and that is VA1 minus VB1 equals VB2 minus VA2. I know VA1 was negative 1.5. If I subtract VB1, which is 6.3, I'm going to get VB2 minus VA2. If I solve for VB2, it will equal negative 7.8 plus VA2. That information can go right there for VB2. The left side over here is going to simplify to 12.99. It will equal VA2 plus 2.3 times a negative 7.8 plus VA2. If I distribute and combine my VA2s, I'm going to get 12.99 equals 3.3 VA2 minus 17.94. I'll add the 17.94 and divide by 3.3 to get that VA2 is a 9.37, or roughly 9.4 meters per second. Because it is positive, I assume that means it goes to the right or the east. So ball A is going to be bounced backwards to the right, or back to the right. It was going left, now it's going to the right. To find VB2, I just need to take the 9.37 and stick it in here for VA2. In this case, VB2 comes out to roughly 1.57, or what we're going to round to 1.6 meters per second. And so ball B also ends up going to the right. So ball B had so much more momentum that it was able to redirect A and keep going to the right. Just got to follow the math on those. Okay, that puts us at question number 5. Question number 5. We've got a vehicle A. It stopped at a light with a mass of 1250. Then object B, car B, is going to rear into it. So I'll put B here. It's going to slam into it. We don't know its initial speed. That's the question. How fast was it moving before the collision? And it has a mass of 1320. We know that afterwards, A and B are going to stick together and move with a velocity of 8.5 immediately after impact. And so this is a stick equation, an inelastic equation. And so, excuse me, we're just going to use momentum. 1320, sorry, the formula is MAVA1 plus MBVB1 equals MA plus MB V2. Excuse me. We don't know VB1, but we know that this guy had a velocity of 0, so it won't matter. And that will equal the combined mass. If I add 1320 and 1250, I get 2570 times 8.5. And then all I have to do is take this value, because the 0 doesn't matter, and divide by 1320. VB1 comes out to be 16.5 meters per second. And then we can debate whether or not that was too fast before the collision on another time. Okay, question number 6 says we're asked for two things. We're asked for the impulse. We're also asked for the force. Okay, so kind of keep those two things in mind. What's the impulse imparted to a 0.145 kilogram baseball that's traveling 45 towards the plate, and after a contact time of 0.013 seconds, it's sent back towards the pitcher at 49 meters a second. Okay, and so we want to know what was the impulse and what is the average force. Well, remember, impulse is often written as delta P is F delta T. Well, there's two things I don't know. I don't know the impulse, I don't know F, and so I can't really solve this the way it is. But I also know this is equal to M delta V. I do know the mass of the ball, and I should be able to determine the change in velocity, which would immediately give me the impulse. So the impulse in this problem is really the mass of 0.0.145, sorry, make that a 1, times the change in velocity. If it was going 45 to the right, then the 45 to the left would be negative. And if we look at the difference in these, we don't think about subtracting. If you think about subtracting, you think about subtracting the negative, which really means to add them. If you add the 45 and the 49, you're going to end up with 94 for your value. And so if we multiply the two of these together, our impulse will turn out to be 13.6. Now, you can put impulse as newtons times seconds, or 13.6, and talk about it in terms of the change in momentum, which would be mass kilograms times meters per second. That is our impulse. Next question is, well, what's the force? Well, if I know that this is 13.6 and I know what delta T is, I should be able to find F. F will be delta P, or the impulse, over the change in time, which is 13.6 over 0.013. So the force turns out to be roughly 1,050 newtons. All right, just a few more. Let's look at 7. 7 says Pascal's principle, how much weight in newtons can be lifted by applying 27 newtons of force to a hydraulic lift with an input area of 0.25 meters squared and an output area of 6 meters squared. If we look at this, Pascal's principle is our Fn, over A in equals F out over A out. Well, the F in was only 27 newtons. We're applying 27 newtons to an area that's just 0.25. We want to know how much can we lift, what force can we lift, or what weight can we lift if the output area is 6. All I have to do is times by 6. This is a really easy question. F turns out to be roughly, after we round, 650 newtons. Question 8. According to the continuity principle, we've got air in an air duct moving through a circular opening, and then it goes through a rectangular vent. And we want to know what is the speed after it goes through the, or as it goes through the rectangular vent. You can imagine there's circular, it's coming along, and then you want it to enter the room, so it has to go through a rectangular opening. And as it goes through the rectangular opening, we experience the velocity change. The rule for this is that we take the area of the first times the velocity, and that should equal the area of the second shape times the velocity in the second shape. Okay, so the area of the first, because it's circular, it says it has a radius, and it says circular. We're going to do pi times r squared. It says it has a circular opening with a diameter of 15 centimeters. That means it has a radius of 7.5 centimeters, or 0.075 meters. Pi r squared times it had a velocity of 18 centimeters per second. That's 0.18 meter per second. So that's area times velocity equals the area of a rectangular opening is going to be length times width. The length of the opening is 18 centimeters, 0.18, times the width of it is 0.13 or 13 centimeters, V2. All I have to do is divide by that value, 0.13 times 0.18, and I get that V2 has to be 0.14 meters per second. And because there were a lot of units in centimeters per second, if you rewrote it as 14 centimeters per second, that would be acceptable as well. All right, last but not least, question number 9. Probably one of the more challenging questions, so pay close attention as we go through it. All right, we've got a pond with a rock inside of it. Okay, I realize I can't lift this rock. It's got a weight of 2,300 newtons. I cannot lift this rock on my own, but I need to get a strap underneath it so I can lift it out of this pond or lake or whatever the case may be. So the question is, can I do that on my own? Am I strong enough to lift the rock, given that the buoyant force is going to help me? There's the applied force. I'm going to apply a force to lift it high enough to get a strap underneath it so that I can lift it with a crane or some other piece of equipment. But the question is, am I even strong enough to do that? Or do I need to bring down some sort of a jack, something to lift it while it's still in the water? And so our question is, what's the applied force have to be? And so we have to realize that if we just do a sum of forces equation, the applied force would equal mg, the weight, minus the buoyant force, because the buoyant force is going to help cancel out some of the weight. I would have to lift the whole rock, but the buoyant force is helping me out, so it's a little bit smaller. That's the amount of force I have to apply. This right here is my winner. Now I know the weight of the rock is 2,300 newtons. I just need to subtract the buoyant force, which would be mg displaced. Okay, I need to know how much water is moved out of the way. Well, we know that the volume of the rock will equal the volume of the water. Okay, that's the key to the whole question. If I can find the volume of the rock, then I'm going to be on my way. So I'm going to come over here and I'm going to work this volume part of the question. First thing I need to know is what's the mass of the rock. Now the mass of the rock is not 2,300 newtons. That's its weight. So if I divide that by 9.8, I'm going to get a mass of roughly 234.8 694. And I'm trying not to round too aggressively along the way. That's the mass of the rock. If I look in my textbook for the density of granite, I'm going to get a value for the density of granite of roughly 2,700. Okay? So that is enough for me to find the volume of the rock or the granite, however you want to label it, because I know the density is mass over volume. If I do the old switcheroo, volume will equal the mass, 234.694, over the density, 2,700. So the volume of the rock, which is the volume of the water that was moved out of the way, is equal to 0.086924. I'll round at some point, but not right away. That is also the volume of the water. Well, if I use this density equation again, the mass of the water would be, if I rearrange this, the density of water, which is 1,000, times the volume of the water, which is 0.086924, and I get that the mass of the water is 86.924. This value can go right up over here as the mass of the water displaced. So now I have 2,300 minus 86.924 times 9.8. When I do that subtraction, I end up with roughly 1450, but for sig figs, I'm going to say, so it's 1448, but I'll say 1400 newtons. That's the amount of force I have to be able to apply. Now, if I can't apply that on my own, maybe just one buddy or two buddies can help me do that as we try to deadlift the rock. If we try to get it out of the water completely, as soon as we start to break the surface of the water, we would see that weight of 1400 newtons for us to lift go up and up and up until we hit 2300 newtons, which would make it very difficult to move it completely out. So that's how we answer those questions. Hopefully that's enough to get you through it, and I'll see you in class.